I hope it's not the same experience you had there, because I need you to understand the zeros and ones. Ones represent what in NIM? Just to recall, a win for the first player or whoever's position it is to play, and a zero represents a loss. Okay, so we know what the zeros and ones actually mean. Good. So first slide. Recall that that's how we represent our win-loss sequence of zeros and ones. There's a lot of open questions left on this problem that are really, I think you just have to fool around with it more. So one of the things you can do is do win-loss sequence, but you can also do a which element you can use to win or lose with. And you would get, if you used like the second element, for example, instead of the first element, you can say I won, and I won with using the subtraction set number 2, the element number 2. So when you create that sequence, that's called a number sequence. And I think there's a lot of open problems on that too. So I'm going to list those along with the other ones, Tyler, finally. I know I'm behind. I need a nudge. So just to remind you, because we had the weekend, which might have obliterated memory, 4, 6 is the subtraction set I'm going to use. I got a pile of tokens here. This is the win-loss sequence. Where does it come from? Well, if I only had one token, I can't, and I'm just sitting with one token, I'm going to lose. If that's what I'm squirreled into. If I have 2, same situation. I can't remove any tokens anymore because I have to remove 4 or 6. I can't win until I'm at the 4th token. If I'm at the 4th token, I can take all those tokens and I'm in a winning position, and so forth. So we create a win-loss sequence. And the idea comes to do this in a way that you're not really thinking about taking away piles. You're just thinking of taking away enough tokens so you can move the other player into a losing position. Right? So I know, for example, that this is a winning position because if I remove 4 of them, I've moved them into a losing position. So the idea is to move your partner into a 0. And today, I would like you to think about, as I'm showing you the theorems, how you can get design the game and structure the game in such a way that you are going to force the person into a loss. Because you know what's going on, they don't. And you can play this in cryptography. So I continued this on. I continued this on for a reason, because what you see is a pattern starts to repeat, and the period turns out to be 8 because that piece that I can copy and paste together has length 8. It's a length 8 string. Thumbs up? Last time I had you make a table. And in that table I asked you, was there anything you could see? And most of you said, well, it looks like the period length is going to be equal to the sum of my 2 elements in the subtraction set. And realize now the subtraction sets can get larger. You can have 3 in them or 4 in them. So we're just playing around with 2 just to see what happens. But in this case, 4 plus 6 didn't equal 8. So we have a problem. So some questions we can ask is, first, does it always cycle? If I do this win-loss position, will it always cycle like this? And if yes, if the answer to that is yes, then can I write down the period as a function of the subtraction set? That general problem is open. That second question is still not known for any, give me any subtraction set, I can tell you what that period is going to be. The first question we can answer pretty easily. The answer is yes. It always does cycle. So I'm going to give you, I told you last time, I'm going to give you a little bit of my history because I feel like the way you might have seen math in all your classes so far is the way you see the calc book, where everything's done, and even our classes are set up like this. I hold the knowledge, I have a suction cup and a pipe that goes to your head, and then you're supposed to open up your mind and the knowledge transfers from my head to your head. That's not the way we do mathematics. It's a bizarre way to teach mathematics because that's not what we do. So for me, it's a creative sport. I'm always thinking, and I get to think about these problems. I love thinking, and so that's where this comes from. So my thinking is polluted by my training. My training was in something called differential equations. And if you don't know what that is, an equation is still the same thing that you knew what it was back when you first solved your first linear equation in high school commutative algebra, where you had linear equations to solve for the x. That's an algebraic equation. And the solution to an algebraic equation is going to be a number. So if you help people with algebra and they didn't get a numerical answer that they circle off, you know that they're very, very lost, right? Because you're supposed to get a number, x is equal to this. In a differential equation, you have a derivative. So this is a derivative. Derivatives you take of functions, right? And the derivative is a direct function of itself. So the solution to a differential equation is the entire function. And differential equations are extremely important because they describe our world. The weather is described by a set of differential equations. Everything's time varying, and they can be derived as functions. Sometimes you can write down the solution, and sometimes you can't. So there's the set of equations that govern the weather. You cannot write down the solution to that. You can only approximate it. And sometimes it's not a good approximation because you'll read something on the weather report and that doesn't really happen. So those are very complicated equations. And hence, we have all sorts of people in this department that study differential equations. We have something to do in case we don't have enough meetings. So for example, you could have that this function is y. So the function derivative is equal to itself. Do you know of a function that does that? Where you take the derivative and it becomes itself again? E to the x. I always use t's because I'm thinking of time. Y of t is, and it turns out that y at 0 is the initial condition. We call that baseline condition or initial condition because these are real applications and you always have to start from somewhere. You already know what baseline is. You know what the baseline weather is today, so you know what to feed into the system. And then you can check, just like you do when you tutor someone in algebra and they get some crazy solution and you ask them, you think that's a solution? Plug it back in there and see if it works. So if you take that and plug it back in there, it works. So that's what differential equations do. You have the solutions in entire function. So that's what I spent a lot of time studying for 5 years at Georgia Tech. And almost every one of the seminars I went to, they had a differential equation. Sometimes it looked like this, sometimes it looked very complicated. And we talk about something called the phase space. That's the world that this differential equation is living in. That comes from the initial condition. The initial condition in this case is a real number. I give it a real number, and then I get the function as a solution. Y0 is so the phase space in this case is the reals. And we're usually interested in what happens as t goes to infinity. We call that long-term behavior or asymptotic behavior. That's what you were usually interested in. If you took a differential equations class, this is what you did a lot of. Okay, so far so good? How many of you took differential equations? Sound familiar a little bit? So I just compressed all of differential equations into about 5 minutes. The bizarre thing about my training is I didn't just study differential equations. I study something called dynamical systems. Anything that evolves in time. Differential equations evolve in time. They're an equation that describes an evolution in time. But recursion equations also do that. You don't know about recursion equations? Anybody's hit the same number over and over on the calculator and pressed a button? That's a recursion equation. You fed it a seed, whatever is sitting on your calculator at the moment. You push the function. You're iterating that function. Every time you push the button again, you're watching where that initial seed is being tracked. So if you start off with a number and hit the cosine button over and over again in the old scientific calculators, it converges. And I learned this back in Algebra 2 because I wasn't paying attention to what I was supposed to be paying attention to, playing with my calculator. So I'm giving you an example of a recursion equation here so you can see one. The n plus first, the next step, is 2 times the previous. And just like the differential equation, an initial conditions given. I got to start somewhere. So if I know where I start, I can give you the next one. Y at 1 is 2 times y at 0 by just plugging into that recursion formula. And I know y at 0, so I can plug it in there, and I get 2 times 1, which is 2. So now I know y at 1. Now I can do that again. Y at 2. Y at 2 is really 2 times y at 1. But I know y at 1 now from my previous work, so I plug that in to get 4. You did this too if you had differential equations. Do you remember where you did something like this? Hmm? No, it looks a lot easier than a differential equation, but you did this in differential equations because a lot of differential equations you can't solve exactly. So you did something called Euler's method, right? Euler's method is recursion. I think of it this way. And for me, differential equations and difference equations or recursion equations are the same thing. And 5 years of that, that means no outside work. You're not allowed to have outside employment in a doctoral program at a tier 1 research institute, right? So all my classes were in a math department. I was in an office with other people in the math department. In the evenings, I went out with the people in the math department. We were just doing math for 5 years nonstop thinking this way. And then I come out to New Jersey. And guess what? No differential equation people hanging with me here. In fact, I was one of the first of the newer people that came to this department. So the older guard wasn't doing this kind of stuff. And I had no one to talk to except a game theorist next door. So that's where all of this is going to come together. So the solution to a recursion equation, it has a solution. It's actually a discrete version of a function. You have a sampling of points. It's the sequence. So you can start to see where NIM may meet differential equations now. You get a sequence. And maybe there's a way to write the whole NIM thing as a recursion. If those of you who are thinking of going to graduate school think that graduate school is any different than what I just described it, it's not. It's exactly that. You're swimming and breathing and learning math. There's a friend of mine who he's trained as a exercise physiologist, and he said, I want to learn all the math you know. And I said, there's no way. You have to start over. Because not only did I do that in graduate school, I continue to do that every day as a professor because I kind of like graduate school, and I thought, I want to do this forever. How do I stay in school forever? That's what I'm doing. So this is really the same thing as a differential equation. I have an equation that governs the behavior. I have an initial condition, the phase space, all of it's the same. But NIM is really different, right? NIM is zeros and ones. So we're getting there. One last thing. In cryptography, I'm sure you're talking about Z2 right now. Talking about finite fields. Z2 is a field. And there's several ways to describe Z2. My favorite way is that it's a packaging. We call it, the formal word for it is partition. You know what Z is. You learn about Z back in 4th grade. Negative numbers, and you have the number line. So this is a number line. That's what Z is. Z is infinite. So what I'm going to do is I'm going to pack up Z into 2 boxes. One box is going to take all the evens, and the other box is going to take all the odds. If I take those 2 boxes and union them up, I get all of Z, right? But the nice thing about this packaging is Z2 only has 2 things in it. And on the box, I'm going to put a label, just like you do when you move your home and you take your boxes out. If you do it right, you say kitchen stuff in here and living room stuff in here. If you do it wrong, you don't have any of those labels. But if you do it right, that's the way it happens. When your houses get bigger, that's what happens. You have to label things. Otherwise, things go into the wrong rooms and make more work. So I'm going to put a little label on them saying 0 is my representative that tells me all the evens are in this box, and 1's a representative that tells me all the odds are in that box. And what's cool is you can add the entire boxes together. Because if I take any of the evens from one box and add them to any of the evens from the other box, I get evens. So evens plus evens make evens. So the 0 box plus the 0 box gives me back the 0 box. The 0 box plus the 1 box gives me the 1 box, because if I take any even number and I add it to any odd number, I get an odd number. 1 plus 1, well, odds plus odds, what do you get? Evens. So odds plus odds give me even boxes, and 1 plus 0 is it's commutative. It works the other way around. So we drop the boxes and we just write Z2 is equal to this 0, 1, and you have an addition table, and I didn't go through the multiplication table. If you didn't take abstract algebra yet, this is the opening to abstract algebra. They talk about these other kinds of sets that you're not used to. What's cool about Z2, it's my favorite field. because I can't make a sign error in it. There are no signs. And in fact, in the paper that I submitted that I'm going to talk about here, the reviewer said, you know, you watch your signs. Like, I don't have to. I'm working on Z2. Z2 is what we call a field. So if you haven't taken abstract algebra yet, you did talk about fields in linear algebra. They've talked about the matrices over fields, and they talked about the scalars, multiplying by scalars. Those are fields that you get the scalars out of. So you can think of scalars. Fields have certain properties. They're like the ultimate thing, the ultimate object in abstract algebra. What's cool about it is it behaves like R. So Z2, all the stuff you learned about R works for Z2, even though it only has two things in it. And you think that couldn't be that interesting. It is. It actually is. Okay, so I'm going to pause here.